It doesn't say any place in the Bible that if equations of motions have a symmetry, the solution should have it too. As a matter of fact, most of the solutions of equations of motion that you're familiar with in your daily experience have no symmetry. However, if you look at the compact solutions, for example, periodic orbits, they can have a following kind of symmetry, which we'll call symmetry of the solution, or GP. It's a group of, or subgroup of elements of the group that takes any point on this solution and maps it onto another point on the solution. However, the set of these points, or the orbit, is invariant. So you're very familiar with this kind of solutions. I tried to draw one there, but if you have something that looks like figure 8 and you flip it around the symmetry axis, it'll look like figure 8 again. This is the simplest example of symmetry group acting on the solution only as a translation within it. It's really, really easy to understand all this concept looking at billiards, three-dimensional, two-dimensional, three-disc billiard in a plane. But we'll try to illustrate it by the simplest imaginable system, which is a system in which you have state space, which consists of a unit interval, or interval from -1 to 1 on a line, so that any point xn at time n, discrete time n, at this interval has its image, what happens a step time later, as the vertical axis on this graph. This dynamics has an obvious fixed point because 0 maps into 0. So the origin here is a fixed point. And we will draw an unstable map through it, meaning a map whose slope is larger than 1, so nearby points separate. And we'll design it in such a way that there is an interval which is mapped by the central map from the interval to entire interval, and then we'll complete it by two other maps, the left and right defined on the left and right interval, but we'll make them symmetric, such that if you flip this picture over its x-axis and z-axis, you get the same picture back. It has a fixed point. As you notice, it actually has two more fixed points. One at -1, -1, and the other one at +1, +1. This interval, which I'll denote C, has a property that in one iteration points on its spread over entire state space. So this map forward in time maps that interval. Does that also for the left interval and for the right interval. So forward in time, it's 1 to 1, but backward in time, it'll be 1 to 3, depending where you came from, which neighborhood. It's not an invertible map. It's a perfectly good model for many dynamical systems. So this fixed point belongs to the interval C. We'll denote it with C above bar, saying that if you iterate and iterate, you stay in C. So it's an infinite sequence of C's in dynamics, if you label this interval by letter C. And C is a fixed point of the group action, because the group is the dihedral group, symmetry group is the dihedral group 1, meaning it just consists of identity element and the flip that sends positive part of the axis into the negative part of the axis. And C is a group invariant or group fixed point solution. So the invariance, the symmetry of that solution fixed point is the entire group. However, if I look at the left fixed point or the right fixed point up there, the group does not leave either one invariant. What it will do, it will map the lower point fixed point or right fixed point. So they together form an asymmetric pair of solutions, which as a set of solutions is invariant, but each solution by itself is not invariant. Under the group it's equivariant. It gets mapped into equivalent solution by the group action. To find more solutions, look at the diagonal and observe that there is a solution which jumps between the left branch, goes onto the center, and does it again and again and again. So it's a two-cycle, period 2 orbit. And the 2 points in this period are inequivalent because symmetry doesn't relay them. Now, what I haven't drawn yet, but I'll draw a little bit later, is another 2-cycle in which one jumps between left and right branch. That cycle, when you flip it, not drawn yet, but will be shown later, has a property that it is itself, or it's self-dual on the group action. So as a set of points, its symmetry is the full group again. This is a very simple case, so the symmetry is either a full group or trivial. And that's, of course, different between action on the two fixed points. This part I'll just have to slice out. It's a nonsense. Cut. Throw this away. Start again. This time I'll attempt to draw the correct 2-cycle, which is self-dual. So you start on left branch, you go out there, and by hook or crook, a very bad picture, should be on the diagonal. You end up on the right branch and you come back. Or it should be on anti-diagonal. Now this guy is self-dual under action of the group, which means under the flip in this case. It's a cycle which we'll denote by 2 letters, left and right, which consists of 2 points. The left, one that maps into the right, and right one that maps into the left under one iteration. And other dynamics, then they're closed. We put the overbar on the LR, meaning that this now repeats forever. The symmetry of this cycle is the full group. Identity and flip. So this is an example of symmetric solution or a self-dual solution. A solution which is invariant under the action of the whole group as a set of points. Now let's look at some other solutions. I'll draw this bimodal map one more time. You can think of it as consisting of three branches, left, center, and right. It acts differently on the three intervals. And this map is invariant because if I flip it on the x-axis, apply the map, and then apply the inverse, which in this case, sigma itself is inverse, I get the map itself. So that's an example of dihedral group 1 symmetry of dynamics. It has a fixed point, which is a fixed point both in time, but it's also a fixed point of group action, because it's left invariant by the entire group. Here it looks very humble, but when you get to fluid flows, for example, this will be called the laminar solution. It'll be a very important solution. And here are two fixed points. You stay in a right upper corner or left upper corner forever. But what the symmetry does, it just flips one into the other. So solutions are either invariant under the action of group, in which case you just have one solution, or they're equivariant, they map into each other, in which case you have a pair of solutions because the order of this group is 2. If the group was, for example, acting on 6 slices of a pizza, the order might be 6 or maybe even 12 if there is a reflection included. So if you find one of such solutions, you will immediately find 6 or 12 equivalent ones. I cheat a little bit. I can just trace out the previous map. And I still don't make it look anti-symmetric under the flip, but you can imagine what's going on. And here's an example of a less trivial solution at a fixed point. It's a 2-cycle where you hop between the left and the center branch. Now this solution is asymmetric. The slopes at the 2 points are different. So being at XLC or XRC gives a different contribution to stability of the orbit, for example. And in time it's an infinite repetition, so we say it's CL bar, meaning infinitely repeated, but all it does is just hops between 2 points. And so what happens next? Instead of killing myself by drawing it again, what I'll do is I'll take this piece of paper and flip it twice, meaning I rotate it, in this case, by 180 degrees. And now this orbit gets a new name. You go from center to the right, and it's not the old orbit. So there are two period 2 cycles, which are related by the flip, by the action of the group. So this is example of two non-trivial solutions which have no symmetry. They are asymmetric. So all the group does, it produces 2 copies, or in general it produces as many copies as there are elements in the group itself. For 3-disk system, it would produce 6 copies of the same solution. So that's an example of asymmetric pair of solutions. So we have solutions which are invariant under group. Fixed points of both group and time dynamics. They're quite isolated and very important. Here it's just center, but because it's one-dimensional dynamics, just a point. In high-dimensional dynamics, there might be a high-dimensional subspace with lots of interesting stuff going on within it. Then there is a world of solutions which I call symmetric or self-dual. And what you notice in this self-dual solution has 2 points, but they look equivalent. If I rotate by 180 degrees, they map into each other. That's what dynamics does with them. And then there are pairs of asymmetric solutions, which we already showed in terms of cycles. So here is a cycle. It's a symmetry partner. Together they are invariant sets, but they are 2 distinct solutions. Disconnected, you can go from one to the other under dynamics. So that's the simplest classification of solutions.